you with some general notions of robustness that you might find helpful in your own work. I'll be talking about experimentation and design in a fairly broad sense. One has some input variables X, some outputs Z, related through a parametric model, which may or may not be entirely accurate. And so okay, our design, the choice of the points X at which we'll observe Z, we hope will be both accurate and efficient. However, that will depend on the accuracy of the model that we fit. Okay, it's been known for, well, over half a century now that a design which is optimal for a model which is even slightly right, I'm sorry, slightly wrong, maybe much less than optimal at the true model. And so the idea here is that the experimenter will fit his assumed model. Okay, this is not about his trying to choose a better model. He believes that the model he has is right. However, he will admit that it's maybe only an approximation of the true state of affairs. Okay, and that there are more accurate models in some small neighborhood of the one that he fits. Okay. What?
I think you should.
It's not the right button.
You should use that one.
Apparently, it won't work on a PDF file.
No, it works, but it's not the right. Can you help me?
I don't know how it works either. So.
No, not this one. No, it's got this, it's not the top button. The top button.
I think we need more expert help here.
We need a woman.
I wonder if it only copies the first page of my. Maybe we should try running it straight off of my memory stick.
Yeah.
Okay. Okay. Let's just run it off my memory stick. Okay. I'll also be talking about estimates obtained through quantile regression. So here's the definition of the regression quantile. It's the quantile in the distribution of the response variable at a particular value of the input variable. And with my colleague Ling Long Kong, I recently obtained designs for quantile regression in approximate linear models, which is a notion I'll describe in a few minutes. Okay, and these are easily modified to apply to nonlinear models. Okay, a part of the motivation for our work is some work that Holger did a number of years ago, Holger and one of his students, on the design problem for quantile regression, only without worrying about the robustness aspects. They assumed that the model they had was exactly the right one and got optimal designs in that case. So why quantile regression? Okay, well, our reason is that it's naturally robust against outliers in the Y space. Okay, it's not robust against outliers among the X's, but okay, if we're choosing the X's, that's not a problem, right? And if the X's are outliers, it's because we want them to be. And it's robust against non-normality, and in particular, there aren't any moment assumptions required. Okay, so it's an attractive alternative to least squares, which has become more and more popular in recent years. Okay, so let's assume now that the tau quantile that we want an estimate of is possibly nonlinear in some parameters. Okay. Well, it's easy to make a nonlinear problem into a linear problem. Okay, if we expand around some prior known value of the parameters, obtaining a linear model, and those two formulations of the model have the same asymptotic properties. So when we do that, okay, F0 here is the response evaluated at the local parameter. The elements of, or small f0 here is the gradient of f evaluated at the local parameters. Okay, and y is the residual from this initial estimate f0. So in that way, we get a model which is approximately linear in these new parameters. Okay, and that's then exactly the framework in which Ling Long and I worked in our paper. So the mathematics we did in it, okay, applies almost wholesale in this nonlinear situation. Okay, and as an example here, I'll illustrate our methods using an example which was also mentioned in the work of Holger and Trampish. This is an experiment by Cressy and Keatley, where it's relating estrogen to amounts of hormone, and the chosen response was a Michaelis-Menten. One of the purposes of this paper was to look at a number of linearizing transformations which are appropriate in the Michaelis-Menten model. And the one they chose was one that was new to me. Okay, here I've always just used the fact that in this notation 1 over z is a linear function of 1 over x. However, this transformation is another possibility which is much less obvious. However, it's the one they chose in the end. And if you use it and then do a least squares regression in order to estimate the intercept and the slope, and then recover the betas, this is what you get. Okay, now is that an appropriate initial estimate if we're doing quantile regression? Okay. Well, okay, it's an appropriate initial estimate if you're doing least squares estimation of the mean response. Okay, and if the errors are symmetric, okay, that would be estimation of the median, okay, which is a quantile, of course. Okay, and so it ought to provide a reasonable initial estimate in that case. And as will be seen, okay, all of the designs we're looking at here are actually independent of the value of tau. Okay, so, okay, this would seem to be a reasonable place to begin. And here's what happens when you use that initial estimate. It's not a great fit. And, it's an indication that we maybe should be looking for robustness of some form. Okay. Here is the gradient in this linear approximation. Okay, so from here on we're talking about things in terms of the new variable y and these regressors. And as a design space, okay, we'll take a number of equally spaced points spanning that interval, out of which we will choose a design of size 20. Okay, so that is the model that the experimenter will fit, and here's how he calculates his estimates. Rho here is this so-called check function. So for instance, if the two linear pieces each had slopes of minus a half and plus a half, we'd be estimating the median. If rho of r was r squared, we're back in the case of least squares. And in the one I've illustrated here, that will give you the 0.95 quantile. Okay, but now the model we fit is only an approximation in a number of ways. Maybe just as a result of the fact that it's a linear approximation of a nonlinear model. Okay, but, well, and maybe as a result of a bad choice of an initial parameter. Okay, or maybe our initial model, the Michaelis-Menten choice, was not entirely accurate. Okay, so there's a number of ways in which we might be looking for, a class of nearby models. And in fact, the class in which we will work is this. Okay, we add a small disturbance onto the response that the experimenter will fit. We call that a model error. Okay. And we also allow for errors which are not equally varied, okay, by introducing this variance function, sigma squared of x. Okay, well here, okay, it's not clear what that parameter even means anymore, okay, because we've added on this extra term in the response. So here's how we define the true parameter. Okay, it'll be the value that will make the model most accurate in the sense of minimizing this quantity. Okay, well, you go through the calculus and you do the minimization, and you end up, well, after a first order approximation, with the requirement that up to a multiplicative constant, the regressors and the model errors, okay, are orthogonal in this sense. Okay. I'll explain in a minute why I put the root n out in here rather than leaving it outside. Okay, this is an orthogonality requirement which is reminiscent of least squares regression, yes, where the residuals and the regressors are orthogonal when we do a least squares regression. Okay, here it's the model errors and the regressors which are orthogonal. Okay, so what we want a design which is robust against the increases in the mean square error, in particular increases in the biases. Resulting when the model we fit is not entirely accurate. Okay, so those can arise okay, either through these errors in the mean or the errors in our assumption that the random errors are homoscedastic. Now, when I put that root n in here, okay, from here we do things asymptotically, and okay, the parameter estimates, the variance of the parameter estimates, we know will drop at the rate 1 over root n. Okay, we're looking at the mean square error, which includes the square of the bias. And so the square of the bias is going to have to drop at the rate 1 over n as well. Okay, otherwise, in the limit, the mean square error is only variance or only bias. So assume that when you multiply the model errors by root n, okay, there is a limit, and that limit is bounded. We place a bound on its L2 norm, okay, for some constant eta. Okay. It'll become apparent in a little while that we don't have to actually choose eta. And okay, we'll also place a bound on the magnitude of the variance function, and we can assume that that bound is 1. Okay, if it isn't, it can be absorbed into the variance of epsilon. Okay, so the overall aim here is to get the mean square error of the estimates, maximize it over this small class of model errors, and then find a design which will make that maximum mean square error a minimum, okay, a minimax design. Okay, the loss is actually the average mean square error evaluated, okay, asymptotically. So here's the true quantile. Okay, here's our estimate of it, okay, which ignores the model error. Okay, so here is, well, the normalized mean square error, which we average over the design space and then evaluate, okay, asymptotically. And this, of course, will all depend on the design, which I'll represent in this way. Psi I is the fraction of the observations that are made at a point xi. Okay, so we evaluate that mean square error, and over the next 1 or 2 slides, I'll explain how it is that the maximum of that is a constant. The constant is independent of the design, so we don't really have to worry about it. Okay, which is why I said initially that these designs are independent of the choice of tau. It just appears as a multiplicative constant out in front of everything else. Okay, and the rest of the loss is a mixture of 2 things. I'll explain on the next slide exactly what those are. But okay, there's a trace of a certain matrix and the maximum eigenvalue of another matrix. And it's a mixture of the 2, and the mixing parameter, okay, includes okay, all these constants, which we don't have to know, okay, because well, the interpretation of the loss here is that, okay, the trace here arises only from the variance of the estimates, and the maximum eigenvalue arises only from the bias. Okay, and so nu represents the faith you have in the model that you fit, and you're able to choose that, okay, without having to know any of these other terms. Okay, so okay, for instance, when Holger approached this problem, he would have chosen nu equal to 0, okay, because he had absolute faith in his Michaelis-Menten model, and he wasn't worried about the bias. Okay, on the other hand, if you are looking for robustness over this range of nearby models, you'd choose a positive value of nu. Okay, so what are these individual terms? Okay, they're all defined in terms of these matrices. Okay, A here looks like the usual X transpose X matrix, okay, in regression, except it's evaluated over all the points in the design space, not merely those that are actually used in the design. Here we are using only the points that are used in the design, okay, and they're weighted by the standard deviation. Okay, and these other matrices, well, are variations of that one. So, okay, the trace here, okay, arises, as I say, only from variation. Okay, that quantity, okay, F transpose S, F is the asymptotic variance of the quantile estimate. And so you average that over all the points X in the design space. Use the usual properties of the trace that allows you to switch things around, and that's how that matrix A enters into things. Okay, and so, as I mentioned, what I call a classical design, in other words, one in which there isn't any aim for robustness, would aim for minimizing L sub 0. Okay, now this other term is the bias term. Okay, you look at the bias of the estimate. I've written that out here. And, well, I think it's kind of obvious you can write that as the product of a vector C, depending on X, and a vector D, which has in it the delta zeros. Okay, we want to maximize over those. Okay, we're maximizing our bias, and the bias is a result of these model errors delta 0. So, well, we're actually maximizing the squared bias, because that's what appears in the mean square error. So, if we square this and average it over the design space, okay, and we end up with this quadratic form in the D's. Okay, and we want to maximize that. Okay, well, remember we had a bound on the deltas. Okay. Okay, so maximizing this over a sphere, this automatically makes you think of maximum eigenvalues. Okay, but it's not quite the maximum eigenvalue of that matrix, because we also had this orthogonality requirement, okay, that the deltas okay, and the regressives are orthogonal. So it's okay, the maximum eigenvalue of a matrix closely related to this one, and in fact it's that one, AT, after you write down the details. Okay, and then we choose nu according to the amount of faith that we have in our model. So we then have our maximum average mean square error, and that has to be minimized now over the design weights. Okay, and here's where the numerical work begins. Okay, we looked at a number of designs. Okay, and actually, we looked at all the designs that there were on this problem, namely ours and Holger's. Okay, and I should add that the designs that Holger and Trampish got were aimed only at the minimization of the variance. Okay, and even there, the variation, isn't measured in the same way that we're measuring it here. They looked at the generalized variance, the determinant of the covariance matrix, and they minimized that, whereas we've looked at the average variance of the predictors. So the aims, were rather different, and to make comparisons of the designs, is a little unfair. But as I say, these were the only other designs out there. So the ones we looked at were, well, the equally spaced design. That's always an easy one to throw in, easy to calculate, and well, I'll say a bit more about it in a minute. In our designs, there was one that minimized the average mean square error. So it will minimize this. For various choices of the variance function. And here the minimization was handled through a genetic algorithm. So there the computations were rather lengthy. We also looked at a problem where we also included a minimax problem over the variance function. We assumed that the variances were powers of the design weights, and then we maximized over R, and then we minimized the design. Well, as it happens, the worst R here is R equals 1. It's always pleasing to get a nice easy answer like that in these problems. And then, well, you can do most of the minimization analytically. It turns out that the optimal design had to have a port of size n. Like the equally spaced design, but the locations are different. And those we found through an exchange algorithm, and found very quickly. The exchange algorithm in this application was very efficient and very quick. We also looked at these designs of Holger's and his student. One of them assumed that the errors were equally varied, and the other assumed that there was a variance function of this form. Remember, F0 is the first order expansion around the local parameter. So we calculated the designs and assessed them, and well, this is a comment I made a minute ago that so when nu equals 0, we're only looking at the behavior against the variance alone, hoping that the model we fit is exactly correct. And there, of course, that's where the d-optimal designs ought to excel. And if they don't here, I think it's only because, as I say, we're measuring the variance in a different way. We're using the average variance rather than the determinant. So here are the designs. One for Holger and Trampish. Have replicates of size 1/2 n at these points, in the case where the errors are equally varied, and at these under that alternate variance function. Ours, well, here's what we get when we use nu equals 0 in the computations. It's as though the replicates here were each split into 2, but at approximately the same locations. Here was the case where we also did minimax over the variance function. okay, and the replicates were split, well, into clusters of size 1/2 n each, but still in the same locations, or approximately the same locations. As we increase nu, so placing more and more emphasis on the reduction of the bias, okay, what happens? And in these problems, this is a feature that we run into repeatedly, is that the clusters get spread out more and more. Okay, so even at nu equals 1/2, okay, all of the frequencies here are 1. Okay, we no longer have any replicates. They're all clusters. And when nu is equal to 1, the extreme where all the emphasis is on the bias, then okay, you get a maximal amount of spread of these clusters. Okay, so how do they do? Here we're looking at the maximum average mean square error, okay, plotted against nu. So again, when nu is equal to 0, we're only looking at the variance. Okay, our designs are the red and the green lines, and in places where you're not able to make out the green line, it's because it's plotted right underneath the red one. Okay, the blue line here is the equally spaced one. Okay, in other words, the uniform design, and it's always kind of a reliable workhorse. The uniform sort of plays the same role in robustness of design as the median does in robust estimation, in that it's highly robust, if not terribly efficient. Okay, and that's what we see here. Okay, it isn't ever very efficient right at nu equals 0. However, when you include the bias in the mix, it always, at least holds its own, it seems. Okay. The other designs at nu equals 0 are all very close. Okay, and we were, pleased that as you move away from 0, okay, and begin to look at these alternate models and take account of the bias. Okay, in most cases, if anything, our loss became even smaller. Okay, so all in all, we were very pleased with the performance of these designs. Just a few comments to wrap up here, and I hope some notions that you might be able to take home with you. And that's that. Okay, if the model is in doubt, then okay, incorporating these notions of robustness can pay off greatly in terms of reduced mean square error, even in small neighborhoods of the model that you fit. And in cases where there already is a classically optimal design, which, okay, I mean, all of you here have lots of these cases of classically optimal designs. Okay, and if you want to build in a little robustness, without having to do a bunch of mathematics or computations, okay, a rough rule is, merely to take your replicates and spread them out into clusters at nearby points. Merely that. okay, is enough to build in some almost automatic robustness. If you are willing to go through more analytical and analytic and numerical work, the designs we got using the exchange algorithm, okay, were much easier to calculate than the Minimax designs, and in almost all cases here, there was hardly any difference at all in the performance. So, that's your next easier alternative, I think, in that case. Okay, thank you for listening.
Any questions or comments?
Well, of course, you still have your parameters, designs a function of the parameters, and one suggestion for implementing a optimal design that is a function of the quantiles is to use the up and down designs that target the quantiles, like the biased coin or some of the others, and they will naturally naturally cluster around whatever percentile you say you want them to go to. And so it would be interesting to know, of course, I mean, they form like a little unimodal distribution, whereas your clusters are all of the equal frequency. But they provide a way of approximating what you're doing, and it would be interesting if there could be some relationship specified.
Yeah.
Because it would say then how you could actually try and do something like this.
Yeah.
We can talk later.
Yeah, thanks. So I'll look into that.
So can you restrict? I mean, you made some robustness against L2 norm of the bias. And I think for these examples, if you have these curves which are very smooth, this is not the appropriate thing. I think you should somehow get robustness against the derivative or something like that. Because right now you try to gain robustness against these wiggly curves if you do this L2 thing. And that's not appropriate, because in these applications, I think it's pretty clear that the curve is smooth, so you should somehow incorporate derivatives.
Well,
That might be more difficult.
okay, the L2 norm of the bias entered in there only because we were looking at the mean square error, okay, as our loss function.
Oh, but you took this sum delta 0 xi squared less or equal than. Anyway, we can talk later.
Yeah, okay.
All right, so for the sake of time, let us move to the second speaker and thank Doc one more time.
Thank you.